Hello, good afternoon. Peter Thomas from Control Specialists. This is the final webinar that we're giving on behalf of the PAA, the PROFIBUS Association of Australia. Those of you that have seen them all, we started off with EMC and industrial automation, and then we went through several webinars associated with design, diagnostics, and gateways in PROFINET networks. Today, we're basically moving completely over to PROFIBUS, and in particular, PROFIBUS surge protectors. The reason that we're doing this is not necessarily to give you an in-depth knowledge of surge protectors, more importantly, the effect that they can have when you are trying to qualify a PROFIBUS network. Some of this has got a slight UK perspective to it, but lightning is lightning. So what I would state is make sure that you check your own local standards as far as surge protectors are concerned, but the principles are the same. Basically then, what I will be showing you shortly will be our live demonstration network, which consists of a PROFIBUS master and several PROFIBUS slaves that are using lightning surge protection as part of that segment. At the moment, I've got them here in my hand. They're clearly the type that you plug in. So these, luckily, the reason I'm using these is that they plug into a DIN rail mounted holder that is a make before break connector, so that when these are removed, then the circuit is maintained. So shortly you'll be seeing our network with the electrical waveforms as they stand, and then I'm going to show you what happens when we plug these in. Now, this is not specific to these particular types. This is any kind of lightning surge protector, and in some respects, it's made easier by using these kind of guys. So basically, that's the idea of what we're going to do today. So let us make a start on here. Let me just go on here. Okay. Let's move that. Okay, there's a little bit of a delay. Here we go. Right, fine. So here is the presentation. As I mentioned earlier, this is being recorded, and a copy of the PDF presentation for this will be given to you. And if you're interested in seeing the recording later on, then just give us a shout and we'll give you the link to it. So basically then, as some of you will be aware, we spend half of our time teaching this kind of stuff, the other time spent on site fixing problems and qualifying networks. Now we're looking specifically at PROFIBUS. So just to remind you that they were the webinars, they were all recorded. If you didn't see them, then you can contact me or contact the PAA for links and details of them. So here we go. As I mentioned, a slight UK perspective initially, just to kind of set the ball rolling. Bottom line is this document here, BS 7671, is the document that all electrical people have to follow when they're doing electrical installations in the UK. And it's very specific, but it also applies to people working in industrial automation, as well as those guys working in ordinary private housing. So in other words, fitting bathrooms, fitting kitchens. A lot of this document won't apply to those kind of people, and it's up to these to decide whether or not each part of it is applicable to them. So basically in here, it talks about, there's a section, protection against transient overvoltages of atmospheric origin or due to switching. In other words, lightning or switching mechanisms. And basically, they're saying that if you are working in an industry where one or both of these are likely, and that you need to be aware of the consequence of these, and that is it could result to serious injury or loss of human life. It could result in an interruption of public services or damage to cultural heritage. It could result in an interruption of commercial or industrial activity. And it could also affect a large number of co-located individuals. And it then goes on to reference two other standards where more information can be found. And I would imagine that this is the situation worldwide, in that we, rather than actually print absolutely everything in one standard, very often these standards have what's called normative references. And that is, in order to conform to this standard in the area of section 443, you really need to be looking at these two others. Now, again, I'm aware that these are European standards, but we will shortly be going into an international section, and then we'll finish off the bits on the standards. So basically, there's two that we're particularly interested in, 50174, and we covered that to some extent in the EMC awareness webinar a few weeks ago. But also we have another one, 62305, and I'll briefly just go through this. And this is basically what they have to use in the UK and the European Union. And this standard breaks the protection of lightning into the following parts: general principles, risk management, physical damage to structures and life hazard, and electrical and electronic systems. I'm not going to go through all of these, don't worry. I'm just trying to set the picture, if you like. So basically, what 62305-2 is talking about is risk management. In other words, how much risk is there of our system being affected by this, and what are the consequences? And first of all, this standard defines the following attachment points for a lightning strike, and it gives them a prefix beginning with the letter S. It talks about flashes to structures, flashes near a structure, flashes to a line, a cable, and flashes near a line. They have to decide, what are we dealing with here? Then they look at the types of damage that can result, and they're categorized with a prefix of D. And we talk of D1 being death or injury to people or animals, D2 being physical damage to buildings and infrastructure, and D3, the failure of electrical and electronic systems. We then have to consider the types of loss. And each type of loss on its own, or a combination of others, could produce some kind of consequential loss. And they categorize these as follows: loss of human life, loss of a service to public, loss of cultural heritage, and loss of economic value or activity. These are all the potential consequences of not putting in lightning surge protection when it's required. So basically, having considered all of them, these three factors, basically, there is a risk that can be done, worked out following a formal assessment. And that's basically all that I'm going to say about lightning surge protection in particular. If you're interested in this and want more information in the background, although this has got a European stance to it, this is a very good document that's available free of charge. DEHN, D-E-H-N, these are one of several manufacturers that make lightning surge protection, and they produce this particular document. So I'd bring your attention to this if you want more information about lightning surge protection in general, although it has got a bit of a European slant to it. So let's get on to the crux of this, lightning surge protection devices. This international standard, 61643-1, looks at the performance requirements of surge protection devices for low voltage power systems, and it defines three types of surge protection devices, or SPDs as we refer to them. And these are type 1, which is protection against direct lightning strikes, and they are generally protect against dangerous arcing and fires. We then have type 2, which are indirect lightning strikes, and they're generally going to ensure long-term maintainability of the system, or the equipment is being protected. And then we have type 3, protection against switching over voltages. And when you look at the catalogues for these manufacturers, there are many, many, many of them. So clearly, if it's not obvious to you which one you need to seek advice. But there are devices specifically for use in the Profibus world and the Ethernet or industrial Ethernet world as well. And they vary in shape and sizes. Some of them are plug-in type, so there is a base in which they plug into. Some of them are more of a kind of a bulkhead mounted device, which is a permanent part of the network. So I've not got a feel of whether one's better than the other. Clearly the idea of putting in is a little bit better from a maintenance point of view, and may have advantages when we're qualifying the network, as you will see shortly. So first of all, one of the whole idea of these surge protectors is to divert any lightning strike and the currents associated with them to ground, to earth. And the problem there is that we are very dependent on the quality of this bonding system. And we talked about this at length during the EMC awareness course a few weeks ago. And basically, the whole idea of where industry is going now is to try to develop a mesh bonded network where basically this network, this bonding network, meets the requirements of safety, EMC, and lightning surge protection. So again, there is a link between EMC and lightning surge protection, if only to do with the bonding aspects of it. And be aware, there's little point of investing in a lightning surge protection if the bonding system is inadequate. You're only going to know this when there's a strike, so you better be looking at it. And there's lots of information about what you need to do and how to go around designing these kind of things. So let's go on to Profibus surge devices then. They're available for Profibus DP, which is fundamentally an RS485 network, and Profibus PA, which is a Manchester bus-powered network, but also many, many other networks as well. They generally, in the case of Profibus, they're generally installed in series with the equipment that we're protecting. So this simple diagram shows two zones: lightning zone 0, was the unprotected side, the side that is potentially at risk from lightning strike. It then goes through some boundary, presumably the wall of the building that contains the equipment. There is then a lightning surge protection device, which has got a connection to the equipotential bonding system. And then you've got the protected network on the right-hand side. Now, the general story about these surge protection devices is that they are transparent. Clearly, there is no software associated with them. The PLC doesn't know about them. They are, as it says, they are transparent. So therefore, this shouldn't be something that we need to consider when we're qualifying the network. And I'm going to show you that is slightly different. Okay, so basically, I'm going to be specific with the range of surge protectors from Dane purely because they're the ones that we happen to be using. I've not got any particular preference. We don't sell them or anything like that. So basically then, they look like this. On the left-hand side, we have a base. That is wired in, and its default state is that there is continuity between the protected side on the bottom, which is the lightning zone 0, and the lightning zone 1, and at the top is the unprotected side. So there is continuity. It's almost as though this device is not there. We've then got the lightning surge protector itself, and as I showed you, these are approximately 40 mil high, 50 mil, maybe slightly less deep, and about 10 millimeters wide. And then they plug in, and you can see that they're DIN rail mounted devices and very easy to install. They're almost fit and forget, if you like. You can just about make out on the side, there is quite a number, for a small device, quite a number of rating information, and it's possibly worth just having a look at what that is, basically. And although there's many numbers associated with these, from my point of view, the ones that you're particularly looking at, and you can see this with reference to the photograph on the right, first of all is the type, 1, 2, or 3, as we've just mentioned. There is then a UN, nominal voltage, and it's the nominal voltage of the system being protected. So if you actually just look on there, 5 volts. Well, basically, those of you that have work on Profibus will know that typically we are looking at between 4 and 7 volts on a Profibus system. We have then got the maximum voltage. This is the maximum voltage of the system being protected. This is 6 volts in this case. We then have the nominal load current, and this is the current that will be handled under normal operation with the network all connected up, being protected. And then we have the final one, which is the lightning impulse current. And this is the maximum amount of current that this surge protector can withstand based on a standardized impulse shape. And this is where it gets a little bit techie, a little bit confusing, but basically there is an international impulse shape that you will see here. And what we have is, you can see on the table, two columns. It starts 10 over 350 and 8 over 20. And these are international ratings of surge protecting devices. The 10 is basically the duration in microseconds to the peak of that current. And the value of that current is shown as I max. In other words, in this case, 100 kiloamps. The 350 is the time that the lightning surge current will decay to 50% of its value, and then it's telling you that that is 50 by definition. So type 1s are usually standardized by an impulse current shape of a 10-350 format. The type 2 are an 820, and that's shown at the very bottom left. And the 8 is the 8 microseconds to a peak, and the 20 is the 20 microseconds to the decay to 50%. The only things that's going to change between every type 1 and every type 2 are the absolute values of current, but the actual 10-350, the 820 remain the same. And again, if you want a bit more background, plenty of information on this. I just wanted to give you a feel of where we are with all of this. Okay, so what about where we put these? And when I've been going around on sites, there's various locations. The bottom line is, from a European standpoint, it states that the lightning surge protectors should be installed as close as practically possible to the boundary between the two zones. Now, that is open to interpretation. Ideally, it should be actually installed in a self-enclosed metallic structure on the wall itself. But there's clearly a cost involved in that. And my experience is that although I've seen that, and although I've seen it recommended, it's not a legal requirement. And most installers tend to put these inside the panel, maybe at the bottom of the panel where the cables are coming in. So again, no legal requirement, but check your own local standards and regulations before taking this as being gospel for your area. In this particular case, though, a device will offer protection for any equipment up to 10 meters downstream of it. And this is all associated with resonances that can take place in these cables. As I've mentioned, in reality, many users prefer to install the surge protection device in the panel for economic reasons, amongst other purposes. In buildings that have a formal lightning surge protection, then the surge protection at the boundary has to be a type 1, otherwise a type 2 should be fitted. And again, be aware that I'm quoting here a European standard. Nowadays, many surge protectors are basically a combined lightning current and surge protection device, which by definition meet type 1 and type 2. So basically, we're going to look at a couple of Dane Blitz surge protectors that they call the Blitz ductors 920271 that they are recommending for use in PROFIBUS DP networks. Now, before we go on to the lightning surge protection, I need to either tell you or remind you of the consequences of reflections in a Profibus network. If you're involved in the support of Profibus networks, you will know that reflections are probably the biggest issue on Profibus networks, and really is what gives Profibus a bad name as having one of it ropey, a lack of robustness, etc. Basically, what reflections are is they are a distortion in the electrical waveforms. We would like nice square waves, ideally, that you're going to see shortly. We can withstand quite a significant amount of distortion, but when it gets so bad, then we have a problem, and then we either get intermittent or permanent network outages. One of the most common areas of or one of the most common causes, should I say, of reflections are the start and end of every segment. But fundamentally, what they are caused by are changes in impedance in the transmission path. That basically is bad connections, damaged cable, wrong cable, use of electrical connector block, etc., etc. And significant reflections can be caused by failing to apply an end-of-line termination at the start and end of every Profibus segment. Basically, a Profibus DP cable has got a characteristic impedance of 150 ohms. So as long as the signal traveling down that cable sees 150 ohms, all meter after meter after meter, he is happy. However, when he gets to the end of the segment, it suddenly goes to infinity. And literally the signal will bounce back, it will reflect back. So the only way we can sort that out is to terminate the transmission path with a resistor or a resistor network as close as possible to the characteristic impedance of the cable. And in the case of Profibus, it's 150 ohms. We have to do it at both ends because it's a bidirectional network. And we normally do this via the dip switches on the Profibus connectors. And you can just see here, there is a red connector that needs to be turned on. It's just worth noting that in Profibus, it's a powered termination. So it's not only a matter of switching in a bank of resistors that collectively come to around about 150 ohms, but there's a 5 volts signal across it to bias the line. But basically, this is quite straightforward. Flicking switches, we can soon check whether we've done that. Most of the problems moving forward tend to be deterioration in the network or a poorly installed network in the first place. So basically, one of the things that we have to do when we're supporting a network is we have to look at the electrical waveforms. And here's an example of an RS485 waveform. RS485 is what's called a balanced differential network, which basically means that we have a signal on both the red and the green, and they're a mirror image of each other. Normally, although we're interested in those individual voltages, we normally look at the difference between the two, and that's what you're seeing here. So we get a plot. Is this acceptable? Well, basically, this is the definition of acceptability is shown here. That basically we are starting off around about 1 volt, plus or minus 0.1 of a volt, which is basically the bias provided by the end of line terminator. So that's always a good indication of whether your line is terminated correctly. We would like nice vertical lines on the transition from a 0 to a 1 and from a 1 to a 0. And we'd also like no ringing when we start to settle out. And this ringing tends to be evidence of reflections. And we put a limit of about 0.5 volt. It's worth mentioning, though, that if you are using the bus analyzers that have a small spur line, they can cause a reflection and you should be really ignoring them. That's kind of known about. It's when the waveform is much more distorted. We also provide a basis of acceptability in terms of the differential voltage, in that we want between 4 and 7 volts. It will work below 4, but from a design point of view, you shouldn't be accepting it. So there's the waveform that we are looking at from an RS485 point of view. When we are auditing a Profibus network, we are looking at 2 things. We're looking at the logical aspect, which is basically the telegrams, making sure that there are no errors, making sure that they're not corrupted, making sure that there are no retries, and so on and so on. But we're also interested in the electrical side. In other words, we're interested in looking at the waveforms. And basically, most of the issues that we're going to get, even if they're seen as a logical issue, they generally are associated with some physical problem. Most will be reflections, occasionally they will be EMC. And as I've mentioned, reflections, basically waveform distortions caused by a change of impedance in the transmission path. So we have to remember then that in Profibus DP, we're using a characteristic impedance of 150 ohms. In Profibus PA, it's 100 ohms. So we have to terminate with a 100 ohm resistor. Any change from this in a given segment can result in reflections that, if they become large enough, will cause network outages. So we're now coming to the crux of the demonstration. What you're seeing here is a schematic of the demonstration network that we use as part of our training and when we're demonstrating Profibus. Quite a busy network, but basically what we've got here is we've got a PLC up here and a backbone comprising of devices. All of these are housed in a single assembly. You can see we've got an Henderson-Hauser field gauge, a ProCentec Combrix for diagnostics, and then we've got a number of repeaters and hubs, but we end there. We've then got a fiber connection down to another hub in a separate building or separate housing, and also a copper connection down to this guy here, a local remote IO with an end-of-line terminator. Now, all we're doing here is that we've just added this for complexity and to allow us to use various technologies. What I'm particularly interested in is downstream here. And what we've got is that we've got a copper connection, which has created a new segment, which we're calling segment 3A. And I have then, in that housing, I have put a blitz ductor, a surge protection device, but it's not plugged in at the moment. It's only the base, so the continuity is maintained. We then go into this red cable, which is just ordinary Profibus cable, but I've shown it as red to try and indicate that this is the cable that's at risk from lightning strike. And then we go into another lightning surge protector because it's going into another building. Now, originally when I did this, the B2 hub to the right of that bottom surge protector was not there. It is there now because I was having a discussion about this. So basically then what I'm going to do is I'm going to switch cameras in a minute, and you're going to see a little camera view of this area around here, but you're also going to see the electrical waveforms. I'm using a Profibus DP analyzer. It's the ProfiTrace analyzer by ProCentec that you may be using yourself. And I'm going to initially connect it here. In other words, I'm plugged in to this DP connector here so that I am looking at this line here, all the way down here. When you see that, I'm then going to relocate it, and I'm going to put it up there on the main backbone, up at the PLC, mainly trying to simulate what somebody who's not that conversant with networks, Profibus networks, and thinks that, oh, well, I'll just plug it near the PLC and I'll get a report, that'll do. So when you see what you're going to see, initially, you're going to see the electrical waveform at point 1 with the surge protectors disconnected. So bear with me a minute while I switch my camera over here. So here we go. Right. Okay, so you hopefully will be seeing now. Let me just check myself to see what you're seeing. You're seeing part of a screen, which is the racks themselves. So let me just get rid of that. And I now just need to bring open my ProfiTrace, which is here. And hopefully there you can see that. Right, okay. So you might have heard me mention it's like spinning plates, this. Okay, so basically, hopefully you can all see this. What you should be seeing now is just a camera view or a dual camera view, a small part of our network in the bottom left, and you can also see the electrical waveform. So let's talk about the electrical waveform first of all. This is a typical RS485 waveform, probably as good as you're going to get in the real world. There is evidence of reflections, these little spikes at the top, and they are being caused by the adapter that I'm using. You can just about see the ultra core being connected here. So this is where I'm monitoring. You might also just be able to see the base of the lightning surge protector, one there and one there, and they're clearly not in there at the moment. But if I was looking at this waveform, yeah, this would be fine. It starts off at 1 volt. It's a good differential voltage. It's good. So what I'm going to do now then is I've got these lightning surge protectors, which I will put there. You can see my hand there. Neither of them are in at the moment. What I'm going to do now is I'm going to plug them in one at a time. Now, clearly, the network should be operating with these in situ. And I'm not telling you anything otherwise. All that I'm wanting you to be aware of is the consequence of it when we come to qualify the network. So here we go. Keep an eye on the waveform as I do. So the first one, I will plug this in just very close to point number 1. And as I do that, it's pretty obvious this is not ideal. Just to be complete, I'll do the one at the far end. Like that. And now we've got a bit of a problem. Interestingly, though, we've got a problem that hasn't caused a network outage. In the UK, the water industry in particular are very meticulous in the way in which they have their networks audited, and they'll get a contractor to go out on the site, and then they'll be looking at these reports, and this then leads to a lot of argument. I'm not passing this because it's out of spec, etc., etc. And then the system integrator says, well, look, what do I do about it? I can basically sort the problem out for you by taking the lightning surge protectors out, like I do, like that. What do you want me to do about it? So we've got a bit of a problem. So basically, what we've discussed many times is the way in which we go around this is, number one, you either accept it, but we've got a potential problem, or you potentially do what we have done, and that is that we encapsulate the lightning surge protectors inside a pair of repeaters or hubs. That way, then we are limiting or mitigating against this. But let me just put this back in again. I'll just put one for speed back in. What I'm going to do now is I'm now going to remove this Profi hub. And what I'm going to do, if I can just get it over there, I'm actually going to move it over here, which is where the PLC is. So, and I just want you mainly to concentrate on the waveform. So we'll leave that in. I'm just going to take this guy out, take him out like that, and I will plug him in somewhere on the backbone. Now we've got a problem, because if people are auditing the network from a standpoint of without knowing the infrastructure and the presence of repeaters or hubs, we can be fooled. This looks absolutely perfect, but the lightning surge protectors, as you can see, are still in. And this is the potential issue that we have. So the crux of all of this is not to tell you don't use lightning surge protectors, far from it. It's simply to be aware that you may need extra features in here. Clearly, you could argue, well, if we did fiber, the problem would have gone away, and that would have been correct. However, just to tell you what's going on here, when the water company that I was working with originally contacted Dane, their response was, well, it won't be the lightning surge protector because they're transparent. And well, yes, they are right. They are transparent in that there's no configuration, they're not seen. But the problem is these have a resistance, an end-to-end resistance, and there is a change in the transmission path. So basically, that change in transmission path is causing reflections, and this is the issue that we have. So that's really been the purpose of this webinar, mainly to bring to your attention the fact that these lightning surge protectors can basically cause issues only to when we're talking about the electrical waveform. Now, another way around it is that you may get special dispensation to be able to qualify the network with the surge protectors disconnected. You better get that in writing before you do that. But that's basically it. Not an issue with the surge protectors themselves. It's just a known problem. Don't take it for granted that your electrical waveform will be distorted in the same way. In my experience, it's very dependent on the network, the length of the cable, etc., etc. But you can clearly see the benefit of using hubs or repeaters, because by definition they clean them up. So that is basically it. I hope that has been of interest to you, and it's more importantly been of use to you. This has been recorded. You will be getting a link to or you'll be sent the PDF and a link to this if you're interested. If you've got any questions, you can just type them in the chat window. Just give you a couple of seconds to do that. If not, thank you very much for your time. All the best.